Welcome to our video on the fascinating topic of multiple test correction in the long run. Have you ever wondered how statistical tests can affect the results of your experiments or studies? Over time, perhaps you've encountered situations where repeated testing led to confusing or contradictory outcomes. Today, we're going to dive into the world of multiple test correction and explore its implications on your research. In this video, we'll be discussing what happens when you perform multiple statistical tests, how it affects your results, and what you can do about it. By the end of this discussion, you'll have a better understanding of the importance of correcting for multiple testing and how to interpret your findings accurately. When conducting research or experiments, it's common to run multiple tests to validate your hypotheses or compare different groups. However, performing multiple tests can lead to an increased risk of obtaining false positive results. This phenomenon is known as the multiple testing problem. Imagine you're flipping a coin 10 times. Each time, you get either heads or tails. If you were to flip the coin only once, the probability of getting heads would be 50%. But what if you flipped it 10 times? You'd expect to see some variation in the result. Now, suppose you perform 10 independent statistical tests, each with a significance level of 5%. In this scenario, about 1 out of every 2 experiments would produce a false positive result purely by chance. This is where multiple test correction comes into play. The idea is to adjust your significance threshold, or p-value, to account for the fact that you're performing multiple tests. One popular method is the Bonferroni correction, which divides your desired alpha level, usually 0.05, by the number of tests being performed. To illustrate this concept further, let's consider an example. Suppose you're studying the effect of a new drug on blood pressure and perform 10 independent tests to evaluate its efficacy. Without any correction, each test would have a 5% chance of producing a false positive result. However, using the Bonferroni correction, you'd divide your alpha level by 10, resulting in an adjusted significance threshold of 0.005. This adjustment helps reduce the likelihood of obtaining false positive results across multiple tests. However, it also makes it more challenging to detect true effects, as the bar for statistical significance is set higher. To summarize the key points discussed so far, multiple test correction is essential when performing multiple statistical tests. The Bonferroni correction is a popular method for adjusting your significance threshold, or p-value. Correcting for multiple testing helps reduce false positive results, but may also make it more difficult to detect true effects. The results of multiple test correction in the long run are crucial for researchers and scientists to understand. By acknowledging the potential pitfalls of repeated testing, you can take steps to adjust your analysis and ensure that your findings accurately reflect reality. We hope this video has shed light on this critical topic. If you have any questions or comments, please don't hesitate to share them in the section below. Be sure to like and subscribe for more content on statistics, research methods, and scientific inquiry. What are some of your favorite methods for correcting multiple testing? Share your experiences with us.